Okay, in the last video, we introduced this idea of Lagrange multipliers to help us solve a certain optimization question. So in this video, we're going to look at the method in more generality, and then we'll solve question 5 on the worksheet. Okay, so here we have a function optimized, and I'll refer to this function f of xy as the objective function, and we're subject to a certain constraint. And we'll describe this constraint by the equation g of xy is equal to c. Okay, so in the last video, we were looking to optimize production F subject to a certain budget constraint, right? And we described that budget constraint by an equation of this form. Okay, now over here in this picture, okay, we have our constraint curve. That's this curve in red described by the equation g of xy is equal to c. And then in green, we have some various level curves of our objective function f. And since we're subject to this constraint, okay, we are looking at points that are at the intersection of these level curves and our constraint curve. And if I want to optimize our objective function f, in particular I'm interested in the level curves, right, of largest or potentially smallest output that still intersect our constraint curve. So in this picture, right, I'm interested in this point right here in yellow that lies on the constraint curve and on this level curve where f is 6. And I'm interested in this point in yellow along this level curve where f is equal to 3. Okay, so these are the level curves that achieve a maximum and a minimum value respectively that still intersect our constraint curve. Okay, so I note here that if the objective function f has a max or a min at the point P subject to this constraint, notice, right, like we saw in the last video, these level curves will be tangent to our constraint curve. They come in and just kiss the constraint curve in one single point. So as a consequence of that, if you effectively just turn 90 degrees, right, if we look at the gradient of f, well, we know the gradient is orthogonal to this green level curve. And if we look at the gradient of g, well, it's orthogonal to this constraint curve, right, because it's a level curve with the function g, right? Since green is tangent to red, turning 90 degrees, that says, well, these two gradient vectors must be parallel. So put another way, and we'll assume for the moment that the gradient of g at p is non-zero, that implies that the gradient of f at p is equal to some scalar multiple of the gradient of g at p. Okay, and we refer to this scalar multiple, lambda, as a Lagrange multiplier. Okay, so here are the key steps in solving a constrained optimization problem. Okay, we're going to find all points P with coordinates x, y that satisfy these two equations, right? So we need the gradient of f at x, y to equal this scalar multiple lambda times the gradient of g at x, y. And, right, we of course need to be on the constraint curve, so our point x, y has to satisfy the constraint equation. Okay, so after we find all points P that satisfy these two conditions, we're then going to find the corresponding function values, right, for our objective function f at these points from step 1. The largest and the smallest of these function values will be the max and mins of our function f subject to this constraint. All right, so now let's go ahead and illustrate that with question 5 on the worksheet. Okay, so here we're told that the sum of the squares of two numbers x and y is equal to 4. Our job is to find the maximum possible value of the sum x plus y. All right, so we can set this up as follows. The function we're trying to optimize is the sum x plus y. Okay, so I'll call f of xy the objective function, that's x plus y. Now, what's our constraint? Well, we're told that the sum of the squares of x and y is equal to 4. So in other words, x squared plus y squared is equal to 4. So I'm going to describe the constraint as follows. G of xy is equal to 4, where g of xy is the sum of the squares of the numbers x and y. All right, so now let's go ahead and illustrate this with a picture. So our constraint curve, right, x squared plus y squared is equal to 4. That's just a circle, right, a radius 2 centered at the origin. And here I've just included a whole bunch of level curves, right, which just happen to be lines in the plane for our objective function f, okay? So again, we're looking at the places, right, where these level curves are tangent to our constraint curve, okay? And to find those, right, we're going to set things up as follows. We find the gradient of f, well, that's just 1, 1. Find the gradient of g, that'd be 2x, right, differentiating this with respect to x, and 2y. And then the two equations, right, that our points have to satisfy, right, are this equation, right, we need the gradient of f to equal lambda times the gradient of g, and this equation, g of x y is equal to 4. That's just the constraint equation, right? Which again is just x squared plus y squared is equal to 4. All right, so now let's go ahead and solve. So going from equation 1, right, gradient of f is 1, 1. That has to equal lambda times the gradient of g, that's 2x, 2y. So now if I go ahead and equate components, the I component on the left side is 1, and the I component on the right side is, if you distribute lambda, 2 lambda x. Equating j components, I get that 1 is equal to 2 lambda y. Okay, now notice here, lambda cannot be 0. Why is that true? Well, if 2 lambda x is equal to 1, and lambda were 0, I have a problem, right? 1 would be equal to 0. So lambda is a non-zero number. All right, now notice 1, 1, right? 2 lambda x and 2 lambda y are both equal to 1. And so that implies 2 lambda x must equal 2 lambda y. And since I know that lambda is non-zero, I can go ahead and divide both sides by 2 lambda, and I find that x must equal y. All right, so now what do I do with that condition? Well, remember, the point we're looking for also has to satisfy our constraint equation. So I go ahead and set x and y equal to one another in the constraint equation x squared plus y squared is equal to 4. Right? So I get x squared plus x squared is equal to 4. That tells me that x is plus or minus root 2. Since x and y are the same thing, y then must also be plus or minus root 2. So I get these 2 points, right? And I see them up here, root 2 comma root 2, and negative root 2, negative root 2. Okay, so what does that tell us? Well, if I go ahead and look at the values now of the objective function at these 2 points. So f of root 2 comma root 2, well, that's just the x plus the y coordinate, right? So root 2 plus itself, that is 2 root 2, all right? If I look at f at this other point, negative root 2 comma negative root 2, that would be negative 2 root 2. Okay, so as we said just a few moments ago, right, this value, since it's the largest of these function values, that is our maximum possible sum for x plus y, and that's what we're ultimately asked to find. We also note here that the minimum possible sum, right, is the negative 2 root 2, but in any event, that does it. All right, I'll see you in the next video. We'll look at another example using Lagrange multipliers. Thanks.